So some of the things that we had talked about, last time, I think I had opened that up. So I posted this, in D2L for our last class. So we had just kind of discussed, what were the A and the B values, what period does, a tangent function have, which tangent has a function of pi, but, we have to basically calculate what the vertical asymptotes are going to be, because the way we define tangent function, and, we had kind of looked at this with our definition of the tangent function here. So the idea is, since we define tangent as, sine over cosine, wherever your cosine function is going to be 0, your tangent function is going to be undefined. And that's actually where we have those vertical asymptotes. And if you remember, we talk about vertical asymptotes in our college algebra course. So we're bringing that same concept over here with our trig function. So the idea is, basically you have to remember that a tangent function has a period of pi. Wherever you have your vertical asymptotes, those x values are not going to be included in your domain. So you can see when we define our domain, this is basically for the tangent function. So we are saying all x values except where you have those vertical asymptotes at, and you will see in this table, this is where, we will have these undefined values, because that's where that denominator of your function is becoming 0. The range for your tangent function is going to be negative to positive infinity, and then just some other information. So when you are trying to define where your vertical asymptotes are going to be, we actually need to use these two equations to try and figure out where those vertical asymptotes are going to be. So the idea is, if this is the basic form of your tangent function, then for the vertical asymptotes, we can use this two equations. So let's take a look at our function over here. This guy is number 16. We are given y equals negative 1/2 tangent of x. So as you can see, as we had identified last time, our a value is 1/2, b value is 1, which is the coefficient on your x term. Now to find our vertical asymptotes, so what we're going to do is, remember they said use bx minus c equal to negative 1/2, and bx minus c equals positive 1/2. So, for our function, your bx minus c is just going to be this x value. So honestly, all you are doing is taking that x value and setting it equal to negative 1/2 and x equal to positive 1/2. So, obviously we have no equation to solve in this case because you already have x by itself. So they by default tell you where your vertical asymptotes are going to be. So if you remember, when we were talking about our sine cosine functions, we were talking about, creating those 5 key points that kind of help us, where the intercept is, where the maximum, minimum values are. So we're still using that same concept here with the tangent function, but the way the tangent function looks like, you're actually not going to have a maximum, minimum value. So if you just kind of, and hopefully you've seen this in the video lecture, but if you kind of look through this paragraph over here, they're telling you basically halfway between our 2 consecutive vertical asymptotes, you will actually find your x-intercept. So we know right between these 2 values, we are going to find our x-intercept. Basically, the period for this transformation form of the tangent function is going to be, between those 2 consecutive vertical asymptotes. So basically, the period for our function is also going to be between negative pi halves and positive pi halves. We actually do not have amplitude for a tangent function, because just the way the function is defined, you don't really have a maximum or a minimum, because look at this general shape of the graph. We don't have that general shape of the sine or cosine function. So you don't really have a maximum or a minimum value. So your amplitude is not defined. Um, and they're talking about, find where your vertical asymptotes are going to be. We know halfway between that we'll have the x-intercept, and then we can plot a few more points in between those numbers to try and see, what kind of behavior our graph is going to be doing. So that's the same kind of thing we will try and do with our function over here. So, we can create a simple little table for our x and y values. So we know at -1/2, and at positive pi/2, sorry, not 1/2, is where we have our vertical asymptotes. So this is actually where it's going to be undefined as far as the y value goes. So what do you think is going to be the halfway point between -pi/2 and positive pi/2, where we will have our x-intercept at? So what do you think is halfway between negative and positive pi/2? Very nice. Yeah, Alicia, very good. So halfway between negative and positive pi/2 is going to be 0, which means your y value is also going to be 0, because that's where we have our x-intercept. So can you tell me what is between 0 and pi/2 and 0 and negative pi/2? So between 0 and positive pi/2 and 0 and negative pi/2. Very good. Yeah, because all you have to do is think about, if you're going halfway between those two, that will be at pi/4. And on the negative side, that would be negative pi/4. So the next thing I want us to do is plug in this positive or negative pi/4 for our x in this tangent function. And let's see what kind of y value we are coming up with. And you can actually use your calculator to figure that out, because we just want to know what kind of shape our graph will have. So we want to know, what that graph will end up looking like. So let's go ahead, plug it in, and let me see what you guys come up with. Let's start with the positive pi/2 and see what we come up with. So do you have a number for me for the positive pi/4? You came up with 1. Okay, let me check my math then, because that's not what I got. You got 1/2. Okay, so let's see, we've got -1/2. And then we've got tangent of x, which x will be pi divided by 4. Okay, make sure I'm in the right mode. Okay, very nice. So yeah, the first answer I saw, I think, was a 1, but that is incorrect. You should have, and it should be a negative answer. So yeah, it should be -1/2. Very good. And then just change that for negative pi/4, and how will that change our answer? So what do you guys come up with for negative pi/4? Yeah, that becomes positive 1/2. All righty. Very good. So just to get a general idea of what this graph will look like, um, okay, Alicia, very good. Okay, so this will of course be our x-axis. This will be y-axis. And of course, our x-axis is going to be broken up. We have 0. We can do pi over 4, pi halves. So that would be 3 pi over 4, pi, positive pi, and then same thing on the negative side. Okay. Because we do have to graph at least 2 periods. It's kind of nice to have these extra x values in here so we know what that would end up looking like. All right, so we know at negative pi halves, we have a vertical asymptote. Positive pi halves. We also have a vertical asymptote, and then we know our graph has x-intercept at the origin, 0, 0, which is this point right over here. So now you can see with the pi quarters and negative pi over 4, we can kind of see where our graph is headed. So pi over 4, you are at negative 1/2. So actually, probably should go ahead and make our markers on the y-axis. And this will of course just be in terms of 1, 2, and 3. And then this would be -1, -2, -3. So when we're talking about having our point at pi quarters and -1/2, that point is going to be down here at pi quarters and -1/2. And then your other point is negative pi over 4 and positive 1/2. So negative pi over 4 and positive 1/2 will be here. So this graph will actually be going in this direction down here like this. And this part of the graph will be going up, kind of like this. And of course, these arms just keep going up and down. So if you remember about vertical asymptote, when we had talked about this in college algebra, and again, hopefully those of you who also went through college algebra, the vertical asymptote basically blocks your graph from going beyond that line, right? So it's kind of blocking it. So the arm of your graph will just get close to that vertical asymptote and just kind of follow along with that line. So that's why it's not going to cross that vertical asymptote. So the idea is your graph gets really, really close to the vertical asymptote, but they don't touch, they don't cross. And so that's the kind of behavior you are noticing over here. Now you will see this repeating pattern, throughout the shape of your graph. So basically the idea is, we went to pi, actually let's do, this was 3, so this guy would be 5 pi over 4. And then this guy will actually be, let me see. If this is 5 pi over 4, this guy will be technically 3 pi over 2. Yeah. So this would actually mean if we had to do a repetition, you should actually have another vertical asymptote right here at positive 3 pi over 2. So that means halfway between that at pi, you would have your x-intercept. So at 5 pi over 4, you would actually again be at negative halves. At 3 pi over 4, you would be at positive 1/2. So again, your pattern would repeat in this direction. And then, of course, you can extend it out to the left-hand side of your graph also. You don't have to, I'm just kind of showing you, what happens with that repetition of these functions. So that actually means that negative 3 pi halves, we would have a vertical asymptote again. Halfway between that, at negative pi, we would again have our x-intercept. At negative 3 pi over 4, you would be at negative 1/2. Negative 5 pi over 4, we would be at positive 1/2. And again, you will see that same repetition in this pattern happening over here. So kind of like what you saw in your, this shape over here, that is, going to keep repeating between those vertical asymptotes. So you can see how when we talk about these vertical asymptotes, you have that main pi halves, but then we are also adding this n times pi. So you're doing n times pi because remember the period of your tangent function is still going to be pi. Doesn't matter where those asymptotes move, your period stays the same. And n being an integer, it kind of tells you, if n is a positive number, you will be on the positive side. As n is on the negative, is a negative number, then your vertical asymptote will be on the negative side. But this is kind of what your, graph will basically end up looking like. So you should notice how this is actually a decreasing function because as you're moving from left to right, your y values are getting smaller. So this is a decreasing function. And the main reason for that happening is this negative sign on your a value. So that's actually what's making this into a decreasing function. And you can kind of read some of that in the description over here. So just a couple different examples in your handout that you can kind of look through and follow those steps to help you out. Now you can see based on what your bx minus c value is going to be, your vertical asymptotes are going to fall, in different places. So in this example, your vertical asymptotes are at negative pi and positive pi. So again, you can see halfway between that, you would have your x-intercept, and then you can find a couple more points to try and see, where exactly those points are going to fall and what kind of shape our graph will have. So you've got another example to look through over here. Just again, something else to help you out. You can see how that changes your vertical asymptotes, and then you can kind of come up with your graph over here. So this is a paragraph I'm mentioning. We are talking about the graph of your function will increase if your vertical asymptotes, between your vertical asymptotes if the a value is positive, but it decreases if the a value is negative, and that's what we have. We have a negative a value, so that's why our graph is decreasing. And then, they also talk about, you can kind of think of having that negative sign on the a value, which basically creates a reflection in the x-axis. So you can kind of think of it in terms of decreasing, or you can say, it's a reflection because of that negative sign on the a value. They're actually also talking how the period changes based on the b value. So we know when we did graphs of sine and cosine functions where your period was defined as 2 pi over b for the sine cosine function. So in that same way, the period for a tangent function can also change based on the b values. If your b value is going to be between 0 and 1, you will have a greater period than the basic tangent function. When b value is going to be greater than 1, then your period will be smaller. So just a little comparison in terms of how the b function affects your graph. You can also think about those in terms of horizontal stretch or horizontal shrink. So I wanted to see if you guys had any question on this number 16 over here. Okay, so keep in mind the period for our function is still the same. It is still at pi. We've already talked about the asymptotes. I'm not sure if they will ask you for domain and range or not, but just in case they do, remember your domain is going to be all x values except where your vertical asymptotes are. So since and you can just use any one of these numbers. Normally you will see they go with the positive numbers. So our vertical asymptote was at the positive side on pi halves. So you're actually going to say the domain will not include pi halves and any multiples of n times pi. So that's our domain. And then range, for the y values, well, you can see these arms are going up and down. So they are using actually all the values on your y-axis. So as far as the range goes for these functions, you're actually looking at all real numbers. So you're going from negative to positive infinity. So it's really the domain that's going to be affected based on where your vertical asymptotes are going to be. So now let's talk about the reciprocal function for tangent, which will be cotangent. So you will see a lot of similarities in the graph of the tangent and cotangent function. Now remember, we define cotangent as cosine of x over sine of x, which means wherever your sine of x function is going to be 0 at, that's where you are going to see the vertical asymptotes for the cotangent function. So whatever, remember, makes the denominator 0 is going to be undefined, and that's where the vertical asymptotes are. Cotangent function also has a period of pi, and since it's a period of pi, our vertical asymptotes will also occur at an interval of n times pi, where again n is your integer value. But look at for the cotangent functions how these equations change. So for the tangent function, we set them equal to negative pi halves and positive pi halves when we did these. But for the cotangent function, you are actually going from 0 to pi. So those equations will be a little bit different for your cotangent function. But, obviously, like I said, you will see a lot of similarities between those two. So let's take a look at our next example. I'm actually not sure which function I went for over here. Looks like we are actually still doing the tangent function, but you know what? Let's change that to 28. Let's do this. 3 times cotangent of pi times x over 2, and let's see what happens with this one. So let's go ahead and write this down. Okay, so we have y equals 3 times cotangent of pi times x over 2. So here again, if you had to identify your a value, that's going to be positive, 3 the number in front. Can you tell me what our b value is going to be for this function? Looking at the equation, what's our b value here? Yeah, very good. It is going to be that coefficient in front of the x. So in front of the x, we have pi over 2, and that's exactly what your b value is. All right, great job, guys. So pi over 2. So remember, again, to find our vertical asymptotes, we will take pi x over 2. And remember, this is the cotangent function. So again, just to show you, with cotangent, you're setting it equal to 0 and pi. So 0, and then this guy will be pi x over 2 equals pi. So now you want to try and get x by itself. So what do you think those two x values are going to be when you solve both of these equations? So what kind of x value will you come up with? Okay, Abdul Aziz, 0 and 2 is what he has. What did you guys come up with? Billy, alrighty, very good, 0 and 2. So yeah, all you really have to do is, since this is a fraction, honestly, you can just invert that and multiply both sides by 2 over pi. So these guys will cancel out. You're left behind with x, and 0 multiplied with anything is 0. So this guy just ends up becoming x equals 0. And then, obviously use the same technique on the right-hand side. So multiply both sides by 2 over pi. So these guys cancel out on the left-hand side. You can think of that pi as being pi over 1. So technically these pi's will cancel each other out, and you are again left behind with x equals 2. So remember, the general form of the equation is take bx minus c, set it equal to 0. Bx minus c, set it equal to pi. So this is where we are going to have our vertical asymptote. So again, let's do a quick table over here. So at x equals 0, we have undefined. And at x equals positive 2, we will also have undefined, because this is where our vertical asymptotes are. Now for the x-intercept, you have to go halfway between that. So what is your x value for halfway between 0 and 2? And remember, you should be able to do this. 0 and 2 are easier numbers, but what if they were, something with pi in them? You should be able to find that halfway point no matter what your x values are. So yeah, very good. Good job. So at positive 1 will be your halfway point, and that will be y value of 0, because that's what happens at x-intercept. So obviously, then you have to look for halfway between 0 and 1, and halfway between 1 and 2. So halfway between 0 and 1 is, of course, 1/2. Halfway between 1 and 2, you can think of it as 1 and 1/2, or you can honestly think of it as 3/2 also, however you want to write that number. If you want to use decimals, you can do 0.5 and 1.5. So whatever you're comfortable with. Same thing like you did in the previous function. Now take these values of 1/2 and 3/2 for your x and put it into the original equation of y equals 3 times cotangent of pi times x over 2, and try and figure out what those y values are going to be. So, we are doing x equals 1/2, so that would be y equals 3 times cotangent of pi halves, and then for x, you can do 1/2, and you'll repeat that for x equals 3/2. So whenever you have your answers for both of these, let me know what you come up with. And remember, for cotangent, if it makes it easier, depending on what kind of calculator you are using, you can use this idea of cotangent being cosine over sine when you're trying to find this. So just like I said, depending on the calculator you are using. Okay, so let's see, I've got I'm guessing you guys are giving me the positive 1/2 first, since that's the first in our table, as positive 3, and then negative 3 for the 3/2. So positive 3 for this guy, negative 3 for this guy. So let me do just a quick check on these. Alrighty, so once you have these 5 key points, then we can do our graph over here. So let's again start with our grid. We are going from 0, 1/2, 1, 1.5, and 2. And let's do on the negative side. And then let's see, y values, we need to go up to positive 3 and negative 3. So 1, 2, 3, 1, 2, 3. All right, vertical asymptotes at 0. So you actually have a vertical asymptote right here on the y-axis. So I'm kind of trying to do it a little bit on the side of that, so because you won't be able to see it with that line. But this is supposed to be a vertical asymptote right here. And then, of course, at positive 2 also. Now, if you were to move this to the left-hand side, then your other vertical asymptote would actually fall between 0, at 0, and then the other one at negative 2. So this is also where we would have a vertical asymptote. So again, we know halfway between that is our x-intercept. So that would be at positive 1 and negative 1. At positive 1/2, we are at positive 3. So that would be right here. At positive 3/2, we are at negative 3, which would be right over here. And, repeat that pattern on the left-hand side of our graph also. So negative 3 for this point, positive 3 for this point. So this guy will come down this way. And, of course, as it goes down, because it's going to take a while, as it goes down, it will start getting closer to your vertical asymptote over here. And then same thing with this guy. So repeat that same graph. Oops. There we go. Okay. And then this guy going in this direction. So can you tell me what is the period of this function? 3 times cotangent of pi x over 2. Yeah, remember what we talked about period? It is that distance going from 2 consecutive vertical asymptotes. If you're going from 0 to 2, those are your 2 consecutive vertical asymptotes. So you're actually going to have a period of 2. So you will see how our period changes in this example, because where your vertical asymptotes ended up ending. And of course, your b value was pi divided by 2. So it is actually increasing the period of our function. So this guy has a period of 2. Very nice, Abdulaziz. Same thing, if you had to talk about domain like we did for the last example, we would say all x except where you have your vertical asymptote. So since we have a vertical asymptote at +2, you would do +2 times n times pi because, sorry, not n times pi because our period changed. Come on. Because your period actually is 2, so it will be 2 plus 2 times n. So that will actually change based on the period. And then, of course, your range is going to be all real numbers. So you will notice that this graph is decreasing, right? It is going down as you go from left to right. But in this example, it does not have to do with the A value because you can see our A value was +3. This is actually because cotangent is the reciprocal function of tangent. So that's why in general form, your cotangent is actually decreasing. Look at this basic cotangent function. Same thing, it's decreasing because that's what a cotangent function does, since this is a reciprocal of the tangent function. So this is actually its natural state. It is supposed to decrease. So if your A value was negative, it would actually start increasing. So you would actually see that difference between the cotangent and the tangent function. So it's kind of really interesting to see, how different these graphs are when you're talking about these reciprocal functions. So any questions on this example over here, guys? Okay, no questions? Alrighty. Oh, looks like I actually did this on the wrong page. Oh well. I was coming back to 27. So 27, I'm going to skip that because since we already did 28, I think 28 was a good combination of 29 and 27. So I'm actually not going to do 27. You should get practice for that, with your homework assignment also. So let's take a look at 21. Okay, so we're getting into the other reciprocal functions, cosecant and secant. So let's talk about that. So again, just a couple other types of example, guys, to help you with these cotangent examples. So if you've not seen the video lectures, go back and take a look at them again. So let's get into our cosecant and secant function. So remember, again, we define cosecant as the reciprocal for the sine function. So that's 1 over sine. Secant, we can define that as 1 over cosine. So, of course, the idea is wherever that bottom function is going to be equal to 0, our functions will be undefined. So you can see we are talking about the places where your tangent function is undefined is the same place where your secant is undefined, because both of them have a cosine of x in the denominator. So whenever cosine is 0, you have a vertical asymptote. So that's actually going to be same for tangent and secant functions. And obviously you will see the same similarity between cotangent and cosecant because both of these functions have a sine of x in their denominator. So this is, again, whenever sine of x is 0, your function, will have vertical asymptote, or it's going to be undefined at that. Now look at how different your secant and cosecant functions look. Because, these are reciprocals of the sine and cosine function. Now your tangent function, is these vertical graphs of this shape. So, when you do the reciprocal, all it ends up doing is changing the direction of your, these vertical columns. But look at your sine and cosine functions that we saw in the previous section. They are these continuous kind of that wave kind of graph. So when we talk about the reciprocals, you will see in this darker, color, the black is where you are seeing the cosecant function. And same thing over here in the darker black color, you are seeing the secant function. So the idea is, excuse me, when we actually draw the graphs of secant and cosecant function, we actually first start by sketching the graph of the reciprocal function, which means if you're actually trying to graph the cosecant function, you will first start with the graph of the sine function. And then, you will draw the cosecant function based on that. And, actually we do the same thing for our secant function also with respect to the cosine function. So the idea here is wherever you see sort of this hill on a sine or cosine function, that will actually create a valley on that reciprocal function. So you can see if the original function actually has a valley, which is where we normally have that minimum point, wherever you have a valley, that actually becomes a hill on your reciprocal function. So they're kind of talking about how those hills and valleys will be interchanged between the original function and their reciprocal function. So it's really kind of interesting how you go about graphing the secant and cosecant functions. So you can kind of read through that paragraph a little bit to help you out. So let's take a look at an example for this guy. Oh, I forgot to mention the period for your sine and cosine functions was 2 pi, so that period actually stays the same for your secant and cosecant function, and you can kind of see that right over here with this graphs over here. Another thing I wanted to point out, wherever you have these intercepts on the sine and cosine function, you will actually have vertical asymptotes for the secant and cosecant function. So everywhere you see in the sine and cosine function where the x-intercepts are, that's the same place you will actually see we have vertical asymptotes for our secant and cosecant function. So that will be another thing to kind of keep in mind. So they're actually just with this example showing you how you can kind of set this up. So since we know the period of a sine function is going to be 2 pi, we are going to use that idea to help us come up with where the asymptotes are. Another thing I wanted to point out, you are actually graphing this as your original function, y equals 2 times cosecant of x plus pi over 4. But we are actually going to start, you can see, by graphing this sine function over here. So we're literally just changing that cosecant to sine, and we're going to graph that function first. And then we're going to use that idea of, doing the reciprocal and interchanging all those hills and valleys to come up with the graph of the cosecant function. So start by, just like you would do any normal sine function, go ahead and figure out your period interval. So we go from 0 to 2 pi. That gives us a period interval of negative pi over 4 to 7 pi over 4. And then, we come up with our 5 key points to find our minimum, maximum, intercepts and all of that. And you can see in the gray, we first graph the sine function, and then everywhere that you have the intercepts, we have our vertical asymptotes, and then the hills become valleys, and the valleys become hills. So let's try and use this in our example over here. So we're looking at number 21. So let's take a look at this guy here. So for 21, we are given y equals cosecant of pi over x. So we are, like we saw in the example, we are actually going to start by graphing y equals sine. Remember, cosecant begins with a c, so we know its reciprocal is going to become with an s. So that tells you it's going to be the sine function. So we're actually going to graph sine of pi over x. So remember, for this, we have to find out our period interval. So instead of vertical asymptotes, the sine function has a period interval, and this is where we take our bx minus c, set it equal to 0, bx minus c equal 2 pi, because remember, period of a sine function is 2 pi. So that's why you go from 0 to 2 pi. So taking these two equations, what is our x value going to be? What do you get for your x values when you solve these two equations? Okay, let's take a look over here. 0, 2, okay. Let's see, we're trying to get x by itself. So that means we can go ahead and divide both sides by pi, get rid of that pi. Same thing on this other equation. And then let's see, this cancels out. This cancels out. Same thing, division. You have 0 divided by pi, which will come out to be 0. On this side, you have pi on the top, pi on the bottom. So yeah, very nice, Abdul Aziz. You go from 0 to 2. So remember, that is your period interval. So when we do our 5 key points, this is where you do trying to remember what it was called. It's kind of slipping my mind, but the idea is you take the difference between your period interval values, 2 minus 0, the lower and the upper endpoints. And then since we want to break this up into 4 equal parts, you divide it by 4. So that actually comes out to be 2 divided by 4, or 1/2. So then you start with 0, you add 1/2 to it. So 0 plus 1/2 is 1/2. Then you keep going. So 1/2 plus 1/2 is going to be 1. 1 plus 1/2 is 1.5 or 3/2. So that actually helps you come up with the different key point values. So you're basically just taking that lower end point 0, adding 1/2 to it, and you keep adding that 1/2 till you basically end up at the upper limit of that endpoint. All right, now we need to find our y value. So what do you think is happening at this first ordered pair when x equals 0? What's your y value going to be? Are you going to be at intercept? Are you going to be at maximum, minimum? Where are you going to be at that 0? Okay, Abdulaziz, you've got your 5. So you've got intercept, maximum, intercept, minimum, and intercept. And guys, the simple thing is, if you're not sure, just plug it into your sine function and see what you're going to get. So if you have x equals 0, well, pi times 0 is going to be 0, and sine of 0. And actually, you can go back to using the unit circle to come up with those numbers again. So if you take a look at sine of 0, which is going to be this, sine of 0 is 0. So you can definitely use the unit circle to help you out with that. So this guy will come out to be 0 over here for 1/2. So if x is 1/2, you're doing pi times 1/2, which will come out to be pi over 2. So sine of pi over 2 is right over here, which is going to be the value of 1. So this will actually give you a maximum, and you can kind of see, our coefficient in front of sine is 1. So that's your amplitude. So that tells you your maximum is going to be at +1 and your minimum is going to be at -1. So all those tricks you learned in section 1.5, come back and use all of those same ones here. So we're going from intercept to maximum to intercept to minimum to intercept. So, of course, intercepts are going to be at 0. Minimum is at -1. So yeah, very good. Abdul Aziz, that's exactly what you want to do. Now let's do our graph over here. Let's take a look at what our cosecant function will find. Okay. So x and y, of course, we are going to +1, +2. There we go. -1, -2. That's on our y-axis, and then of course our x-axis is going from 0, 1/2, 1, 3/2, 2. So 0 right over here. We can do 1/2, +1, 3/2, +2, and same thing on the negative side. So -2, -3/2, -1, -1/2, and then these guys will be positive. Okay, so let's do our sine function first. So at 0, 0, we have intercept. We have maximum at 1/2, intercept again, minimum at 3/2, and then intercept again. So if we reverse that on the left-hand side, you will actually be at minimum here, intercept, maximum over here, and intercept again. So this is our sine function. So this is how you actually will start. And of course, this guy is going to continue on in this direction. So that is sine of pi over x. So y equals. And since we are graphing both of them on the same coordinate, it's always a good idea to label your graph. So this is going to be y equals sine of pi over x. Now remember what I said, everywhere that you have intercepts, that's where your reciprocal function will have vertical asymptote. So everywhere that you have intercepts, let's go ahead and draw our vertical asymptotes there. So you will, of course, have vertical asymptote on your y-axis also. Oh, what did I do? Oh, hit something. Okay. So vertical asymptote here, and then, of course, same thing on the negative side. Okay. Now, for your cosecant function, which is the original function we are trying to graph, everywhere that you had hills, remember they will become valleys and valleys will become hills. So that means you are actually going to have, you're going to be sharing this common point, but since this was a hill, this guy will actually become a valley, which means it will kind of stay blocked between those vertical asymptotes. And it's going to have a shape like this. So you now have a valley over here. Then our next, we have a valley on the sine function. So that will actually end up becoming a hill on the cosecant function. So this guy will now go down for both your arms. And of course, keep repeating that pattern over the different intervals. And then our last one is going to be a hill. So this is our y equals cosecant of pi over x. That's how you actually graph these reciprocal functions for your cosecant, and you will actually have the same exact process for the secant function, which will come from the cosecant. So what do you think is the period of your cosecant function over here? Because remember, the original sine function has a period of pi, but did that period change? This is for the sine function. But what was the period of this sine of pi times x function? Because that will be the period of your cosecant function. So can you tell me what is the period for this sine of pi times x? Okay, and Abdul Aziz, how did you calculate that? How did you get your period of 2? From the interval, the period interval? Yeah, you can definitely calculate it from that. Very nice. So since your period interval is going from 0 to 2, that tells you you have a period of 2. Or remember, you can also do 2 pi divided by b, and our b value is pi. So you can do 2 pi divided by pi, which will actually end up giving you 2 also. So you can do it from the period interval or just use the formula to calculate your period. So that's actually going to be the same period for the cosecant function also. So this will have a period of 2. So that technically actually means you will have one hill and one valley together to create one period. Because remember how with the sine and cosine functions, we said you had to go from, for sine function, intercept, maximum intercept, minimum intercept to get one full period. So with the cosecant function, that translates to into one valley and one hill. So you can see if we go from 0 to 2, you've got one valley and one hill. So that gives you a period of 2. How would you write the domain for this cosecant function? Because you have to see where those asymptotes are, right? So how would you write the domain for this particular y equals cosecant of pi x? All real numbers except n. So you would say all x except. So you can actually see your first, if you go from 0 to the right, your first vertical asymptote is actually happening at positive 1. So it will actually be positive 1 plus n. And yeah, n can be an integer, so n can be 1. So 1 plus 1 will give you 2, which will bring you to the vertical asymptote at 2. If if n was -1, -1 plus 1 will be 0, which gives you the y-axis. So you're actually going to write it as 1 plus n, or as Abdul Aziz said, I think technically, since this is in increments of just 1, you could say all x except n, and I think that might also work. Okay. How are you going to write the range? Because this graph is very different than your cosecant that we did over here, or tangent, because this was a continuous line that was going up and down. So like you saw over here with the tangent and cotangent, but that's not the case because these are these little curves like hills and valleys. So how can you write the range for this function? Okay, Abdul Aziz, you are going from negative infinity to -1 union positive 1 to infinity. Okay, let's take a look at this graph here. Okay, so we are talking about the cosecant function. Let's take a look at this guy over here. So the reason why we are not including, these numbers which fall between -1 and +1 on the y-axis is because you actually have no graph from that black graph, right? Which is the cosecant function. Because between -1 and +1, you have the sine function, or even if you look at this guy over here, between -1 and +1, you have the cosine function. So you actually have to skip that part. So yeah, very nice. So wherever you see that graph in the blue, you cannot include those y values in your range for the cosecant function. So very nice. We are coming from, this is going down to -infinity. So you are coming from -infinity and you are stopping right here at -1, but we include that because, obviously we do have points at -1 and +1. And then you are moving to the upper half of the graph, which starts at +1. So then you pick right back up at +1. And then, of course, you are headed to +infinity on the y-axis. So you use the union symbol to join the two parts of your range. So it's kind of interesting, based on what the function looks like, your range is going to change. And these range values of 1 and -1 is actually going to come from what is the amplitude of your sine and cosine function. So, whatever that a value will be in front of the sine or cosine function, that's actually going to create that amplitude in our sine cosine functions, but that actually also affects what your range for the cosecant and secant function is going to be. Okay, questions on this one, guys? So remember, again, you are not graphing these by hand, but you will still need to use a lot of these same techniques in your homework or quizzes, because you still have to choose the right graph. So even though they give you those four graphs to choose from, you still kind of have to know how you are going to choose those correct graphs. I think our next example is it a secant? Because I did want to show you what a secant looks like. So let's see what 23 looks like. Yeah, that's a secant function. So very quickly, let's take a look at what the secant function will look like. So we're looking at number 23 over here. So remember, secant comes from the cosine function. So we have y equals 1/2 secant of, oh, that is also pi over x, which is what we had in this guy. You know what? Let's not do 23. Let's do 24 because I don't want to use the same b value. Let's just change that to 24, which will change this guy here to a 2. And this will become 3 times x. Okay. So again, remember, you will actually start by graphing its reciprocal function. So that will be our y equals 2 times secant starts with an s, which means its reciprocal starts with a c. So that will be cosine of 3x. So same thing, you have to take your bx minus c, set it equal to 0. Bx minus c, set it equal to 2 pi, because again, cosine function has a period of 2 pi. So for us, that translates into 3x equals 0 and 3x equals 2 pi. So what are your x values over here? So what will we get for our x. Delete 0 and 2 pi over 3. Alrighty, very good, because again, you're trying to get x by itself, which means we would go ahead and divide both sides by 3. And 0 divided by 3 is 0. Of course, we cannot simplify 2 pi over 3, so that will stay the same. So remember, this is our period interval. So our period interval is going from 0 to 2 pi. Additionally, that means our period for the cosine and consequently secant function is actually now going to be 2 pi over 3, because if you did 2 pi over b, that would end up giving you 2 pi over 3, because our b value happens to be 3, right? All right, let's do our key points. So you are going from 0, and then we'll need to figure out what these middle numbers are, and we should end up at 2 pi over 3. So again, to figure out, what you're going to be doing the increments in, remember, you take the difference between your period interval. So 2 pi over 3 minus 0. You're breaking this up into 4 equal parts. So that's going to be 2 pi over 3 divided by 4. Or, as I always show you, 2 pi over 3 dividing by 4 is the same thing as multiplying by 1/4. So what do you think our increment should be to figure out these key points? 2 pi over 3 multiplied by 1/4 will give us 1. Abdul Aziz, yeah, very good. Oh, sorry, I didn't mean to do that. Because, again, however you want to simplify it, but I look at it and I see 2 goes into 4 twice, so I can actually write this as pi over 3 times 2 is 6. So you are actually adding all of these with pi over 6. So 0 plus pi over 6 is pi over 6. And then, keep adding pi over 6. So this will actually become 2 pi over 6 or pi over 3. Very nice, Abdul Aziz. Then again, add pi over 6 to that. And that will be 2. You have pi over 2, okay? So let me see, that will be 2 plus 3 pi over 6, yeah, pi over 2, and then that should bring you back to 2 pi over 3. So basically keep adding this pi over 6 starting from your left endpoint and keep adding till you get to the right endpoint, 2 pi over 3. And then since this is a cosine function, where do you begin? At intercept, maximum, minimum? Where does a cosine function start at? Because we had talked about this in section 1.5. Okay, so I am noticing Abdul Aziz is really, and Billy are the only 2 people who are really answering. Again, we want to make sure each and every one of you are understanding this. So a cosine function always begins with a maximum. So you go from maximum, intercept, minimum, intercept, and then, of course, you're going to end up at a maximum again. So your maximum, you can look at the A value, which is positive 2 in this case. So that's what your amplitude is going to be. So at maximum, you are going to be at positive 2. At minimum, you are going to be at negative 2. And then, of course, intercepts brings you down to a 0. All right, guys, very quickly, we're already a little over our time over here. So we are going at an amplitude of 2. So just to save some time, I'm just going to do positive 2 and negative 2. And then on our x-axis, we are going from 0, pi over 6, pi over 3, pi halves, and then 2 pi over 3. So those will be the negatives. Okay, so let's see, we have maximum, intercept, minimum, intercept, and maximum. And then let's see, on the left-hand side, we will have intercept, minimum, intercept, and maximum. So this is what our cosine function will end up looking like. And again, just a quick rough sketch. So this is y equals 2 times cosine of 3x. Just like we saw with the sine function, you will see that same thing over here. Wherever you have intercepts, you will now have vertical asymptotes. So intercept now becomes vertical asymptote for your secant function. And then just like you saw with the previous example, hills become valleys and valleys become hills, right? So you have a hill over here, or at least a partial one. So this will be a valley. Where we have a valley, this guy will become a hill. So this guy will now go in this direction. In the middle, this guy will become a valley. He's going to be a hill. And then, of course, this is going to be a partial valley. And this is your y equals 2 times secant of 3x, which was the original function that we were trying to graph. So once you have that basic cosine or sine function, you can see it's literally just inverting those hills and valleys and you get your graph. So really the main calculation happens right here with this cosine and sine function. So we've already got the period for this. We know this is going to be a period of 2 pi over 3. So can you guys just quickly tell me what the domain and range for our secant function is going to be? So for
Mr.
this function. Yeah, you said yeah?
I'm sorry to interrupt, but I have a class in like 3 minutes.
No,
so
go ahead. Yeah, you can just catch up with the domain and range part by looking at the notes, but you can go ahead and leave.
Thank you.
So just quickly, guys, what do you think the domain and range for the secant function is going to be? Because, just like you saw in the previous example, everywhere that you have those vertical asymptotes, we have to remove that from our domain. And then, of course, restrict your range based on what y values you are not using. So if you had to guess, of course, we know it's going to be all x, but then not equal to what? Okay, so Abdulaziz, you've got all real numbers except pi over 6 plus pi over 3 times n. Okay, so this is what Abdulaziz is giving us. So except pi over 6, which is where you can see is where our first vertical asymptote happens in our graph. So that's definitely a good point. And then you are adding a multiple of n times, you are doing pi over 3. So if n is just pi over 3, that will become if it's -2 or if it's +2. Yeah, I think actually that will work. Yeah, very good, Abdulaziz. And then what can we say about the range for this function? What y values are we not allowed to use for the range? So you can kind of see how for this one, we were not including anything between -1 and +1 because that's where you had the sine function. So using this idea of the range, how would you change that for this function over here with our cosine and secant function? Yeah, you are actually, like I said, let that amplitude for the cosine function decide how the range is going to change. The same thing, we're coming from, negative infinity, and you can see we stop right here at -2. But since we have a point over there, we include that. Then from there, you jump up to +2 because that's where this bottom part begins. And then, of course, you are headed in the positive infinity direction on the y-axis and use a union to join the two parts of your range. So it may take some playing around and kind of getting used to with these domain and range, but I would definitely ask you guys to work with that a little bit because you should be comfortable knowing in what intervals those vertical asymptotes are showing and then how that range gets restricted, where that original sine or cosine function is going to fall. So please practice with this. We are actually pretty much done as far as the graphing part goes for chapter or section 1.6. We just have, I think, a couple other different examples I just wanted to show you with word problems and that kind of thing. But so keep working on your homework over here. And Eusebia had to leave, but I will go ahead and open up your 1.7 homework. That is also actually going to be on graphing. So we will talk about how the inverse functions look like. We have actually not talked about inverse functions. We've only done reciprocal. So we're getting into inverse function next. So a lot of graphing in the second half of chapter 1. So if you have any questions, stay back. But if you don't have any questions, guys, I will see you on Wednesday morning. So be careful. Take care, everyone. Stay safe. Bye, guys. Hey, Chris.
Hi,
How's it going?
it's good. I'm good. I just need to log out, so I don't really have any questions. Following it pretty well. I ended up catching a plane ticket to visit my sister, so I haven't had a chance to log in and do as much homework as I planned, but it's good.
Oh, I'm sure that must have been a great break, though, to go and see your sister.
Yeah, it's nice. I have a little niece who is like 1.5, who I hadn't had a chance to meet, and I hadn't got to see my